What if one of the millions of asteroids in our solar system was on a collision course with the Earth? What would we do? How would we react? Hundreds of the world's top engineers and scientists specializing in planetary defense come together to tackle these important questions. Discover the latest alternatives to Armageddon on NASA Edge.
Welcome to NASA Edge.
An inside and outside look at all things NASA.
From the Meteor Crater in Arizona.
And we have special co-host Jeffrey Notkin of the Meteorite Men. Welcome.
Thank you so much. I'm thrilled to be here.
We're here for the Planetary Defense Conference in Flagstaff, Arizona, and behind us is Exhibit A of why we need planetary defense.
And we'll be talking to a number of experts on near-Earth objects.
We should get started on those interviews.
Let's do it.
Hey, let's check it out.
The conference was an incredible think tank with asteroid experts. When they weren't busy attending sessions or presenting papers, we had a chance to talk with many of them one-on-one. Chris kicked things off for us by speaking with Eileen Ryan about how we can discover potential Earth-colliding asteroids.
So Eileen, tell me about NASA's Space Guard program.
NASA's Space Guard program is the term we call the effort from many different observatories in the United States and some elsewhere in the world that looks for objects like comets or asteroids that have orbits that cross the Earth's orbit, such that we might be concerned that in the future they could hit us by us and them being at the same place at the same time.
We have a number of telescopes that are part of this program?
We do. There are about 3 discovery telescopes that survey the night sky, looking for these objects and finding them. And then they pass on the information to a network of 5 telescopes that are called follow-up telescopes.
Okay.
Those telescopes will take the initial discovery and extend the positional information so we can accurately determine an orbit and then assess, is this going to be something that we have to worry about, exactly what the level of risk would be.
The follow-up telescopes, could they be discovery telescopes as well, or are they limited by the size?
Many of the follow-up telescopes do a little bit of discovery on the side,
Right.
but they are primarily limited by their field of view. The survey telescopes have very large fields of view, so they can scan large patchwork quilts of the night sky, where the discovery telescopes have a smaller focus so that they can do more accurate positional studies, as well as trying to characterize the objects that are being discovered. When we find them, we have just their orbital positions, but you might want to know a little bit more about something,
Right.
especially if it's headed right for you. So some of the information we would like to add to that, which is a real advantage for a smaller field of view in a discovery, would be how fast is the object spinning, what is it made out of, what's its shape, and other very important physical parameters like that.
Lance, we've seen a lot of cool things at the Planetary Defense Conference, but you were talking during your session about actually imaging asteroids with radar. Can you tell me a little bit about what you're actually doing to give us these fantastic images?
So there are 2 radar facilities in the world that we use for this. One is the Goldstone Deep Space Network's 70-meter antenna in California, and the other is the Arecibo telescope in Puerto Rico, which is 305 meters in diameter. Both of them have high-powered radar transmitters on them, and they're basically like big satellite TV dishes. They produce a radio signal that shoots up into space. Imagine that this is the asteroid in space and my hand is the radar dish. The signal goes up into space, hits the asteroid, bounces off of it, and then reflects back down. And just as it's about to come down to the ground, we switch from transmitting to receiving, and then collect data for some period of time, and then resume transmitting. It's directly analogous to, for example, turning a flashlight on and off, or perhaps the pop of a flash on a camera, except a flash goes off much, much more quickly. Depending on how we're doing the transmitting, if the asteroid is close enough and the images are going to be really bright, we can basically modulate what we transmit and turn them into black and white images that can allow us to spatially resolve the asteroids. So it's an active form of observation. Most telescopic observations are passive, where you aim a telescope at something and just measure what it is you're collecting. In this case, we're actively transmitting a radio signal. It bounces off the asteroid, comes back to Earth, we make an exposure, and then we transmit again and make another exposure. And we keep on doing that as the asteroid moves and as it rotates.
Just like an asteroid photographer, if you will.
Yeah, you could think of it that way. We're actually getting much more information than just that, though, because the radar measurements that we make enable us to estimate the asteroid's velocity through its Doppler shift, and also its distance. And the measurements we can make are extremely precise. Our best resolution is 4 meters per pixel, which, well, to give you a sense of comparison, I'm about 1.8 meters tall. So this is a little more than twice my height that we can resolve things.
Wow.
And so we do this on a regular basis for objects that are millions of kilometers, or millions of miles, if you would, away from the Earth.
Pretty impressive work from our ground observation stations. Of course, not all observations are made from the ground. Chris talked to David Trilling about using orbital telescopes to track objects in space.
So David, you gave a great talk today about the Warm Spitzer telescope. How do you use that telescope specifically in your work?
We had this big program to observe about 600 near-Earth asteroids, which when the program started was about 10% of all the known near-Earth asteroids. Of course, since then there have been more discovered, so we're not at 10% anymore. For each one of those asteroids, we observe it with Warm Spitzer, and we measure the diameter, and we also measure the reflectivity of the body, which reflectivity tells you something about the composition. So we're basically, for each of these 600, measuring composition and size.
How do you find that those near-Earth objects passing through?
That's actually easy. You point it at the sky, the stars don't move, and the asteroids move.
And you can see that through video, or is that just through data that you collect?
It's through the data. You could imagine, take your digital camera and point it out at the road and take a picture every 3 seconds. Okay. And you'll just see the cars that drive past on the road. It's the equivalent of that.
Okay.
Only we're seeing, points of light that are moving, and some moving this way and some moving this way, and you have to basically connect the dots. And we do that in a pretty sophisticated way, but that's essentially the problem. You connect the dots, you know where the telescope is, you know where the sun is, you know where the dots are, and so you can calculate the orbit for this object.
Right.
And then using some other techniques, we measure the size and the orbit, and then we know the answer.
We have lots of ways to identify different objects in space, and Amy Mainzer talked to our guest host, Jeff Notkin, about how NASA is using all of the data.
So we've used our sample of about 700 near-Earth asteroids to extrapolate what's actually out there. And because we're an infrared survey telescope, we are sensitive to the very light-colored asteroids as well as the very dark-colored asteroids, and that gives us a representative sample, if you will. So if we extrapolate what we've learned from NEOWISE, this is what we found. There's good news and there's not so good news. The good news is that for the really large asteroids, the ones larger than a kilometer, these are the things very much like the dinosaur-killing impactor 65 million years ago. 90% of those, and maybe even more, have been discovered to date. So that's great. And that means that there's very little chance that there's a civilization-destroying Earth impactor out there in the future that we haven't already found. Now, when we get to smaller sizes, which are still quite a bit larger in most cases than the impactor that just exploded over Russia in 2013, for those, the situation is not as good. We have not discovered nearly as many of those. For objects that are about 100 meters in diameter, which is about the size of a football field, with NEOWISE, we found that there are about 20,500 of these objects, larger than 100 meters, and only about 25% of them have been discovered to date. So clearly, there's a lot more work to be done.
I'm sure everybody that saw the recent impact in Russia is asking the same question. How did we miss this one? Our friend from the European Space Agency explained.
As far as space situational awareness is concerned, how was it that no one was able to see the Russian meteor?
The Russian meteorite explosion there had the disadvantage that it came directly from the sun. So just like a good military pilot, this meteorite for some reason decided to come at us from a direction where we cannot look. And luckily it was small enough so it didn't do any real damage. I mean, many people were hurt, so that was bad. Windows were shattered, but it didn't kill anybody. But this object we could not have seen on that approach. We could possibly have seen it on a previous flyby to our planet when it was flying away from the planet. But we heard yesterday at the conference from Paul Chodas that he did an analysis, and over the last 30 years, it would have been very difficult to spot this object.
One of the things I found most fascinating about the Chelyabinsk event was the time delay in this footage that we see the fireball streaking by, and then we're looking at the smoke trail, and then there's the shock wave.
That time delay really is to be expected. It tells us how far away the explosion was. You could use the time delay almost immediately to realize that it was a very high altitude explosion, because it took almost 2 minutes between the fireball itself, the deposition of the energy in the upper atmosphere, and the arrival of the shock wave on the ground. We were probably all familiar with counting seconds after a lightning flash till you get to the thunder, and typically you come up with a couple of miles
distance. Well, in this case, it's more like 20 miles distance because it deposited the energy so high in the atmosphere. And this event is unusual that there was actually a sound. Most of the fireballs that we see, the smaller fireballs, even if they deposit most of their energy at that high altitude, there's no sound on the ground. In this case, there was so much energy released that the wave actually reached the surface in a strong form. We could hear the explosion, windows were shattered, and so on. So it's the magnitude of the event that really is so unusual here.
I'm glad that the meteor in Russia didn't have an impact like the one here in Arizona. Of course, this is a fascinating place to visit, and I was excited to talk about this massive crater with someone who knows just a little bit about meteors. Jeff Notkin, co-host of the Science Channel's Meteorite Men, has spent his career traveling to remote locations around the world in search of impact sites and meteorites. When it comes to meteoritics, he really knows his stuff. Jeff, it's really exciting to actually be here in front of what Franklin calls Exhibit A for our need for planetary defense. But as I understand, the meteor crater wasn't always thought to be a crater. A lot of people thought it was a volcano. Can you tell us about the history?
You're absolutely correct. And the history of this site as it relates to meteoritics really begins around 1903 when Daniel Moreau Barringer came here. And he was a mining engineer, and he was also a visionary. He was a man ahead of his time. He was certain that this was a meteorite crater. And all of the leading geologists at the time said, no, it couldn't possibly have been caused by rocks coming from outer space. It's a steam blowout, or it's a sinkhole, or we're not really sure what it is. But Barringer stuck to his guns, and part of the evidence that strongly supported his viewpoint was at that time, on the plains around the crater, there were many strange twisted pieces of rusty metal, and they were later shown to be meteorite fragments that were the remains of the impactor that caused this extraordinary feature.
Well, I don't know much about meteorites, but looking around, you don't see those big fragments. But are there still smaller fragments around the crater?
There are doubtless still some pieces buried here, and back around the turn of the century and even into the 1930s and 40s, large pieces were found on the surface, and some of them were actually melted down for the war effort during World War II, which was important at the time, but seems kind of tragic to meteorite researchers now, how much material was lost. And so by collecting fragments over the years, scientists have learned a lot about the impactor, but it's very important to note that this is a protected site. This is a unique site in all the world. So you cannot come here and collect meteorites. Anything that remains buried here will stay as it is, so that there will be something to study in the future. And it wasn't much more than 100 years ago that nobody even thought this was a meteorite crater. So look how far we've come. How far will we have gone in another 100 years when we have new technology that can allow us to perhaps examine the crater and any remaining fragments in a different way?
Well, it's incredibly impressive. But the one thing I wonder too, from your standpoint, when you look at something as impressive as this, what can we learn about it scientifically? What can we learn about meteorites and meteors and impacts?
We can learn that we're in danger. And it's a pleasant irony that the Planetary Defense Conference is taking place about 45 miles west of us at the moment, because if you want any evidence that there is a danger of our planet or our civilization being destroyed by impacts from asteroids, here it is. And this is a small one.
Right.
So by studying this crater, by studying the fragments that were recovered in the past, we get an idea of the makeup of meteorites that can cause the most damage. This crater was formed by an iron meteorite, a very dense piece composed primarily of iron with some nickel. And it was traveling with such velocity and carried such mass with it that it didn't experience atmospheric braking like most meteorites do, most potential meteorites. It punched right through the atmosphere and exploded, thereby creating this gigantic and unique feature.
An impact on the order of what happened in Arizona would be devastating no matter where it hit. And that makes this a global issue. Fortunately, global concerns are definitely in Sergio Camacho's wheelhouse. One of the challenges we have is this is clearly a global issue. It's not just a NASA issue, but it's a global issue. How are you involved in planetary defense from a global perspective?
One of the issues that we will have to deal is who is going to act in case there's a threat of an impact. If the impact is not coming to a nation that has the capability to do something about it, the first question is, does anybody do anything about it? And there is a feeling that there's a moral obligation that if we can do something, we should do something. At the same time, then we want to have a universal understanding of what we're doing so that it is not misconstrued that maybe intentionally somebody caused damage on someone else in case that deflection was not fully successful. As long as we haven't touched it, it's what we call an act of God.
Right.
The moment you touch it, you own it. And nobody is going to act if they're going to run the risk of later being accused of improper actions and maybe liabilities.
Deciding to act or not at a point where we're not really sure what we can do is also a difficult question. I mean, in some sense, you've got to tackle a few of these near-Earth objects and try to move them or try to deflect them to even know if you have the capability to do it.
It's something that we have discussed and debated, and we're doing both things. On one hand, we're working on sensitizing the political establishment on what is being done, why it's being done, the threat, the magnitude that it could reach, and the fact that we're looking at what to do about it.
Now, understand that you're working on one of the many deflection techniques that are being proposed if we encounter a collision course with a near-Earth object. What is this technique that you're working on?
Yes, well, one of the techniques we're putting forward is to use the contactless deflection of an asteroid through laser ablation, where we're having a moderately sized or small-sized spacecraft with an onboard laser system, and that laser would shoot against the asteroid, where the absorbed heat of the laser beam would enable the sublimation of the surface material. And this sublimation immediately transforms the sort of rocky asteroid into a big plume of hot gas and ejecta from the illuminated spot. But that's enough to sublimate the surface, creating this plume of ejecta that's very much like a rocket exhaust in standard methods of rocket propulsion. And it's that plume of ejecta that acts against the asteroid over a long period of time to gently nudge it away, so gently push it away.
Laser ablation is an exciting approach to planetary defense. We were also able to learn about how NASA, ESA, and astronomers around the world are sharing their ideas. Alan Harris, an astronomer working with NeoShield, talked about the 3 most popular strategies.
One of these is the so-called kinetic impactor. And it's quite a simple idea in that you take a spacecraft, it's a relatively massive spacecraft, it might be a few tons in mass, and you simply steer it at very, very high velocity into the asteroid. So it's a big collision. And in doing so, you transfer momentum to the asteroid and you slightly change its orbit, right? You slightly change its track or at least its position. There's another technique called the gravity tractor. It's a technique that doesn't involve actually contact with the asteroid itself. So in that case, you take a relatively massive spacecraft and you rendezvous with the asteroid. You don't collide with it, you rendezvous with it, and you bring the spacecraft up to the asteroid, and until the spacecraft comes under the gravitational pull of the asteroid, which of course is very, very small. We're talking about objects of a few hundred meters in diameter. So they virtually have no gravity. It's hardly measurable. But it does exist. There is gravity, and that gravitational pull of the asteroid will tend to pull the spacecraft down to its surface. But the spacecraft has propulsion, it has engines, and you fire the engines to simply keep a constant distance from the asteroid. And as you do that, very, very gently and gradually, it has the effect of pulling the asteroid with it. And so it takes a relatively long time to do this, but the advantage is you can very accurately control the change in orbit of the asteroid. In the case of a very large object, something, for instance, more than 500 meters up to a kilometer, it's highly unlikely that we'd have to deal with something like that. However, you never know. Statistically, anything's possible. If we were confronted with a large object, then the kinetic impactor wouldn't be adequate, the gravity tractor certainly wouldn't be adequate. We'd have to go for our third technique that we're looking at in the NeoShield project, and that's what we call blast deflection.
When you don't have a lot of time on your hands and you got an asteroid bearing down on Earth, that's pretty much your final remaining option, is to blow the thing to smithereens. That's one of the things that we're studying as part of our NIAC, that's NASA Innovative Advanced Concepts study project, and we're designing a hypervelocity asteroid intercept vehicle, or HI-V is the acronym.
Okay.
And so the idea is, if you have a nuclear explosive device, which is what we would be forced to use in a short warning time scenario, those devices contain more energy per unit mass than chemical explosives or a kinetic impact vehicle. We leverage the fact that if you excavate a small crater in the surface of the asteroid and you can place the nuclear explosive in that crater the moment that it detonates, then that's about 20 times more effective at coupling the energy of the blast into the body of the asteroid. And so you can couple enough energy into the asteroid body, and how much energy you need depends on how big the asteroid is, but you can couple enough energy to the asteroid that it just, basically imparts velocity to all the mass in the asteroid and just disperses it into a big cloud of debris.
Now, are you seeing this as sort of as the last line of defense for blowing up an asteroid, or is it?
Sort of. So we're assuming that we haven't discovered the asteroid even exists until roughly about 10 years from when it will hit the Earth.
Okay.
So if we discover it 20, 30 some years or more before it's going to hit the Earth, which is certainly possible, then in that case you can use other techniques. But if we discover the asteroid 10 years or less before it's going to make the hit, then we don't try any of those other things. We go straight to the HI-V option that I've been describing.
Not everything about planetary defense involves deflection or destructive methods. NASA is also planning a mission that will help us better understand asteroids, and Dan Masnick took time to explain it in detail.
It was announced last week in the President's budget rollout, and the focus of it is bringing asteroidal resources, material, hopefully to capture, return a small near-Earth asteroid, and bring it back to cislunar space using a solar electric propulsion spacecraft and a capture mechanism that would grab the object and contain it. Asteroids in general are a synergy for all the different things that NASA works on: science, human space exploration, planetary defense. Obviously, we're at the Planetary Defense Conference, that's important, and resources. For probably as long as I can remember, and it's probably been since the inception of NASA, we've always talked about utilizing space-based resources, living off the land. And one of the fundamental issues with using in situ resources is they're typically done at the destination. So if that destination is Mars, you have to get there. And if you rely on those resources, there's a certain risk inherent in that mission.
Right.
But just as we don't drag a tanker truck behind us when we go cross country, we rely on the gas stations along the way to allow us to make that trip. By bringing these resources back to cislunar space, understanding how we can process and get valuable resources like water in particular, which can be used for anything from consumption by humans to rocket propellant, etc. We can actually bring those resources to the point of departure, utilize them, get comfortable with those operations so that we can change this paradigm and basically be able to use space-based resources and feel comfortable with them.
We'd like to thank everybody for joining us here at the Planetary Defense Conference 2013.
And we'd like to thank Jeffrey Nodkin once again for being on the show.
Gentlemen, it's really been my pleasure to work with you and to speak with so many fascinating experts in the field.
Hey, we learned so much about near-Earth objects this past week, and it makes us realize just how small we are in the universe.
So let's take good care of our planet.
You're watching NASA Edge.